So that means that partial of u with respect to x must equal partial of v with respect to y, and partial of v with respect to x must equal minus partial of u with respect to y. So in order for any complex function to be differentiable, that has to be true. Otherwise, forget it. The derivative won't exist. You won't have a unique tangent line. Game over. So
when you bring those down from the parentheses, the first one is u or v?
oh, that's a u. That's a u.
Okay. Why?
Oh, because f is u plus iv.
Right. Okay.
Yeah, so I have u plus iv here with respect to x, u plus iv here with respect to y.
Okay.
Yeah.
I see.
Yeah. So these have to be true. So, and these are called the Cauchy-Riemann equations. Cauchy-Riemann are two of the greatest mathematicians of all time. It's a shame that Riemann died of tuberculosis at the age of 40.
It'd be wonderful if we can keep all of our brilliant minds alive at least, because then we could have Einstein and other mathematicians still inventing stuff. Because those are the people who really drive civilization, are they not? The brilliant people who come up with massive inventions. Like it was calculus that pretty much led the Industrial Revolution, was it not? Or was it?
Yeah, I think the timing is about right for that. Now, but let's take a closer look at what's going on here with these partial derivatives being equal. So there's two consequences of this. So suppose f is differentiable in a region containing a closed curve C. So this is a curve, it's sitting in a complex plane, but you can think of it as the same old plane curves that we've been talking about, at least visually you can think of it that way. Well, then the integral of f along C, we can write it this way in terms of familiar differential forms. So that would be the same as u plus iv. That's f. And then dz is dx plus I dy. So you can break it up like that, because z is x plus iy. Now, you multiply all this out. So you get u dx so I want to have all right, so plus iv dx plus iu dy minus, because I times I is minus 1, minus v dy. All right. So let's group this together. So we have okay. Actually, what I want to do is group real and imaginary parts together. So now we have u minus v, sorry, u dx minus v dy, that's one integral, plus I, and then we have v dx plus u dy. And both of these are real. What can we do with an integral over a closed curve? How can we rewrite it? what can we apply?
Is it the double integral?
Yeah, which is
Green's
what?
theorem?
Yes, Green's theorem.
Yeah.
Okay. All right. So you guys have just been using it on the test, have you not? So okay. So now you can apply Green's theorem to each of these individually. So let's see what that gives you.
Do you think remembering the names of those are, how important is
That?
The Green's theorem.
Green's well, actually, after today's lecture, it might not be so important after all.
Okay.
Because I'm going to condense them all down to one anyway.
Yeah, that's right.
So, what?
Everything that rises must converge.
Yeah, there you go.
Are you familiar with the book?
Oh, with
The book.
which?
Everything that rises must converge.
Oh, no. All right. So now we apply Green's theorem to this. So suppose that the curve C is enclosing a region D, like before. So now what we're going to have is we're going to have minus V x minus uy dx dy plus I times Green's theorem applied to the other one. So we're going to have ux minus vy dx dy. So what do these turn out to be based on what we saw about these partial derivatives before? Yeah, because ux equals vy. Ux minus vy, that's going to be 0. Here we have vx is minus uy, so v's also cancel. Everything goes away.
So I doesn't matter.
So what?
I doesn't matter?
Right, because if 0 plus I times 0, that's still going to be 0. So what happens is the integral of this differentiable function over its closed curve is 0. We weren't talking about conservative vector fields or any of that crap. It's just a complexly differentiable function. Or on a closed curve, it worked out to be 0. This is called the Cauchy integral theorem. Okay.
And that's going to be, that's generalized to all complex functions, is it not?
Well, any that are differentiable anyway.
Okay.
But there are certain functions that you would think would be differentiable based on your experience in the reals, might not turn out to be differentiable in the complex world. So the condition is stronger. Of course, I remember when I took a complex analysis class, one of the homework problems I was given was solve the equation sine z is equal to 2. So you get all sorts of weird stuff like that. So this is one consequence of what it takes to be differentiable in the complex world. But there's another consequence that could also be described in terms of things that we have talked about. Because suppose you're evaluating a double integral. So you have some function f of xy dx dy over some region D. Now, at this point, we're back in real numbers. All right, but I want to focus on these equations here. So suppose you want to evaluate this double integral by making a change of variable to another region, which I'll call d tilde. So now you have f of x of uv, y of uv, then you have du dv, and what do you have in between that has to go in there to make this change that you dealt with some weeks ago? Well, kind of, but what's it called?